Hello guys, today we will discuss all the questions that have come from analog circuits in 2021 GATE examination for electronics and telecommunication branch. Okay, so there are 6 questions, right? 3 are of 1 mark and 3 are of 2 marks. So total 9 marks have been asked in 2021 for this particular subject. Okay, so we will solve all the question one by one. Guys, see the first question. Okay, in the circuit shown in the figure, right, transistor M1 and M2 are operating in saturation, right? The channel length modulation coefficient, right, of the transistors are non-zero. That means the lambda 1 and lambda 2 are not equal to 0. That means it have finite output resistance in saturation, right? And the transconductance of the MOSFETs. What is transconductance? It is nothing but the change in output current with respect to change in the input voltage of the MOSFET. Okay, are GM1 and GM2 respectively, right? And the internal resistance of the MOSFET. What is internal resistance? It is nothing but the drain to source resistance of the MOSFET. Okay, are M1 and of M1 and M2 are R01 and R02 respectively. That means resistance looking from drain to source of M2 is R02. The resistance looking from drain to source of M1 is R01. Okay, it is asked, right, to find out the small signal gain. Okay, dV out by dV in. Okay, so since it is a 1 mark question, okay, we shall solve in 30 seconds. Okay, first I will tell you how to solve in 30 seconds. Okay, then we will see the detailed solution. Okay, so let us go to the first step. See, when my V input AC is not there, means it is equal to 0. Okay, there will be some DC current ID that is flowing through the transistor M2 and M1. Also, there is a DC voltage at the output. Okay, it is DC. Okay, so when I apply a AC at the input, not equal to 0, right? What will happen? Corresponding to my input AC, there will be a AC current, okay, that will be superimposed over the already flowing DC current, right? So there will be a small AC current, okay. The small AC current is flowing because of when I apply a input AC, okay, that is getting superimposed over the DC, okay. Similarly, at the output also, I will get a DC voltage along with some AC voltage. So when I apply a input AC, I will get some AC current. Also, I will get some AC voltage at the output. Okay. So I have to find out the ratio between, okay, V out AC by V in AC. Okay. So before solving, what we need to understand how the amplification takes place in amplifier. Otherwise, what is the amplification process? Okay, so how it takes place? You see, when I apply a input AC, okay, it goes and modulate my gate to source voltage of the MOSFET. Okay, then there is a change in gate to source voltage corresponding to the change in gate to source voltage. There will be a change in drain current, which is nothing but AC current, okay, that flows through the transistor, which is nothing but the transconductance of the transistor into the change in input VGS. Okay. When this AC current, AC drain current flows through a output node, which is generally high resistance, right? When it flows through a output node, which is generally a high resistance, right? I get a AC output voltage, V out AC, AC. Okay, so what we need to find out, the voltage gain is nothing but V out AC divided by V in AC. Okay, so my input voltage modulate the gate to source voltage. Then in response to change in VGS, I get a AC drain current, okay, which is GM into VGS. Okay, when this AC current flows through a high resistance, it generates a output AC voltage, which is generally higher compared to the input AC voltage. Then I have to find out the output AC divided by input AC. Okay. So first thing is, if you see here, okay, there will be some AC current flowing through the node. Okay. If you see, my V out will be minus ID, okay, into total resistance at this node. Okay, total resistance at this node with respect to ground. Okay, so total R net at the output node. Okay, if you see, when I am doing AC or small signal analysis, I have to make all the DC sources to ground, right? So what is R net? If you see, minus ID is nothing but what it do. See, my V input is applied between this gate of transistor M2 and source of transistor M2. So V input is nothing but VGS2, right? V into ground is nothing but VGS2. Okay. So the current flowing through this transistor is small ID is GM2 into V in, right? This is the current, because when they change in VGS, the current flowing through this transistor is GM into VGS. For this transistor M2, VGS2 is nothing but V in. So the current is GM2 into V in. That is the R out. R out is nothing but resistance at the output node with respect to ground. Okay. So it is composite of two resistance, right? So resistance at the output is the resistance looking upward, right? Parallel to the resistance looking downward. Okay. So I can say R of in parallel to R down. This is my output voltage. So is equal to minus GM2 into V into R of is, I am looking to the drain of transistor M2. Okay. When I look to the drain of transistor M2, the resistance is nothing but R02, right? In parallel to R down. R down means I am looking to the source of transistor M1. Okay. So we will see in the next slide. The resistance looking from the source of the transistor is 1 by GM1 parallel to R01. Okay. This we will see in the next slide. Suppose somebody would have practiced a lot, he could have easily known by now the resistance looking to the source is 1 by GM1 parallel to R01. So now simplest, my voltage gain is AB is equal to V out by V in is equal to minus GM2 into R02 parallel to 1 by GM1 parallel to R01. Okay. So if you see, the option D is the right answer. Okay. Here it is GM1, 1 by GM1 parallel to R01 parallel to R02. Okay. So option D is the right answer. Okay. If somebody did not remember or did not know that the resistance looking downward is 1 by GM1 parallel to R01, and the resistance looking upward is R02. We have to do the detailed small signal analysis. Okay, so we will see that process also. So you see, in this circuit, when I am going to do small signal analysis, right, I have to replace all the DC sources to ground, right? So my DC voltage sources I replaced ground because now I am only interested in finding out the AC quantities or the incremental quantities. Okay, so I make this VDD to 0. Now what I have to do? I have to replace each of the transistor by its small signal equivalent model. Suppose I want to replace M2. Okay, how I have to replace? You see, for M2, see from gate to ground, that means this V into ground, I have a V in, right? So get G2 to ground, I have V in, then source is grounded, S2 is grounded, right? And there is a small signal current that flows GM2 into V in, okay? And the resistance looking from drain to source is R02, okay? This is the small signal model of my transistor M2. Now I have to model, say in the same way, transistor M1. Transistor M1 is source is connected to the drain of transistor M2. So this is my drain. Okay. To this, my transistor M1 is connected. Okay. So this is the model of my transistor M1. Okay. You see, source is connected to drain. So S1 is connected to the D2. This is D2 connected to the S1, right? And gate is grounded. G1 is grounded. The small signal current is nothing but GM1 into VGS1, right? And the resistance from source to drain is nothing but R01. Okay, so this is my small signal equivalent model. Okay, now you see for this transistor M1, what is VGS1? VGS1 is equal to VG is nothing but ground 0 minus VS. VS is nothing but V out minus V out. So I can replace this one by GM1 into 0 minus V out is equal to minus GM1 V out, right? So I have replaced this. Since the current flowing from drain to source, okay, since the current is flowing from drain to source is plus GM1 into VS1. Now I got it after replacing VGS1 minus GM1 into V out. That means current will be opposite, right? Current will be opposite, right? Because the current is minus GM1 into V out, which is should be opposite because here we assume GM1 into VS1 is positive. Now it come negative, so the current is opposite. Okay. Now you see the current is flowing from the output node to ground, right? And the resistance also from output node to ground. So I can redraw the circuit, right? So from output node to ground, a current is flowing, and from output node to ground, there is a resistance R01. Okay. Now you see this branch, the voltage across this is V out, and the current is GM1 into V out. So I can replace it by resistance, right? R is equal to V out is by voltage, current is nothing but GM1 into V out. So it is equal to 1 by GM. So I can replace this branch by resistance of value 1 by GM1. Okay, because the voltage across this is V out, current is GM1 into V out. So it is equivalent to putting a resistor 1 by GM1, right? So I put a resistor 1 by GM1. So now it's very easy to calculate the V out. V out is nothing but minus GM2 into V in, right? Current is coming out of the node, minus GM2 into V in into the resistance this node is nothing but R02 parallel to 1 by GM1 parallel to R01. Okay. So you see, so gain is equal to GM2 into R02 parallel to 1 by GM1 parallel to R01. So by drawing the small signal model, it is easy for us to calculate the gain. So one should know how to draw the small signal models. Okay, so this is the answer. you will get 1 marks. Okay, so we will go to the next question. See, in this question, for the circuit with an ideal op-amp, what is the ideal op-amp? Ideal op-amp have gain is equal to infinity, R input is infinity, output resistance is equal to 0, okay, bandwidth is equal to infinity. All these characteristics are of a ideal op-amp. Okay, what it is asking, Vref is fixed, okay, Vref is fixed, okay, and Vout is equal to 1 volt for Vin is equal to 0.1 volt, and Vout is equal to 6 volt for Vin is equal to 1 volt, okay, and it is asking the value of Rf by Rin. Okay, so now what we have to do? We have to do superposition theorem. First thing is we'll calculate V out only when V in is present. Okay, let it be V out 1. Okay, then we'll calculate V out only when V ref is present, right? Let it be V out 2. Okay, so we'll calculate V out 1 only when V in is present, V out 2 only when V ref is present. Okay, now my V out will be is equal to V out 1 plus V out 2. Clear? So let's calculate one by one. So in this you see, first calculate V out 1. Okay, what is V out 1, guys? See, since the op-amp is in negative feedback, because there is some part of the output getting fed to the negative terminal, right? So it is in negative feedback. Okay, then it obeys a principle called virtual ground. That means V negative is equal to V positive. This will happen when the op-amp is in negative feedback, right? Now we have to calculate the V out due to only when V in is present. Okay, so see, since the current to the ideal op-amp is 0, this is ground, this is also 0 volt, right? So since V minus is equal to V plus, this will also is equal to 0 volt. Okay, so let the node will be X. So let's apply a nodal at the, let apply nodal at X, node X. Okay, so okay, you see what will happen. I am applying a nodal at this point. Okay, 0 minus V in by R in, okay, plus 0 minus V out 1. Okay, V out 1. Okay, V out 1. This is V out 2 by RF is equal to 0. If you solve this, what will get? V out 1 is equal to, okay, minus RF by R in, okay, into V in, right? This is my V out 1. Okay, so now in this circuit, I have to calculate V out 2 due to V ref. Okay, so let the voltage here is V positive, right? Let the voltage here is V negative. Okay, since there is a negative feedback, that is some part of output is getting fed to the negative terminal. Okay, so V positive is equal to V negative. Okay, so now we have to apply a nodal here, right? Nodal here. Let the point will be Y. Okay, so apply nodal at node Y. Okay, what will happen, guys? You see, this is V positive, this is V negative, means this is equal to also V positive, because it's in negative feedback. Because of virtual ground principle, the node potentiality here is V positive. Okay, what is V positive? V positive is nothing but Vref into R2 by R1 plus R2, right? R2 by R1 plus R2. Okay, so now we apply the nodal here in the Y. Okay, at node I Y, the potential is V positive minus this is ground is equal to 0 by R in plus again this potential here is V positive minus V out, okay, by RF is equal to 0. Okay, so this implies V out is equal to 1 plus RF by R in into V positive, right? Okay, so this is my V out 2, this is my V out 2 actually. So now V out is equal to V out 1 plus V out 2. Okay, this implies what is V out 1 is minus RF by R1 into V in plus what is V out 2 here 1 plus RF by R in, okay, into V positive, right? So now I have to apply the conditions. Okay, so let's take this into the next page. So I got V out is equal to minus RF by R in into V in plus 1 plus RF by R in into V positive, right? V positive. Okay, so let us take let, okay, RF by R in is equal to K. Okay, let's take a constant K. Okay, that means V out is equal to minus K into V in plus 1 plus K into V positive. Okay, now there are two conditions, right? What are they? The first condition is V out is equal to 1 volt for V in is equal to 0.1 volt. We'll apply this one. So first condition is V out is equal to 1 volt when V in is equal to 0.1 volt. Okay, this is the condition. We'll apply in this above equation. So V out is equal to 1 volt minus K into 0.1 is the V in, right? Plus 1 plus K into V positive. Okay. The second condition is what? The second condition is V out is equal to 6 volt for V in is equal to 1 volt. So this is one condition. This is equation 1. Okay. The second condition is V out is equal to 6 volt when V in is equal to 1 volt. Okay. This implies V out is equal to 6 volt is equal to minus K into 6. V in is 6. V in is equal to 1. Right. V in is equal to 1. So V in is equal to 1 volt. 1 volt. Okay. Plus 1 plus K, okay, into V positive. Equation 2. Okay, do equation 2 minus equation 1. Equation 2 minus equation 1. 6 minus, this implies 6 minus 1 is equal to 5 minus 1 minus 0.1. That means minus 0.9. Minus 1 minus 0.1 is equal to 0.9 into K plus this both get cancelled. Okay, it is equal to 0. This implies K is equal to 5 by 0.9. Okay, minus, this implies K magnitude is equal to something but RF by R in is equal to 50 by 9 is equal to 5.555, right? So the answer is 5.5.5. This is the answer, right? Very easy, guys. Yeah. Let's go to the next question. In this question, again op-amp is ideal op-amp, okay? And Vin is less than VCC, Vref is less than VCC, right? The condition A2 is Vout is equal to 0, right? So here also you can see there is a negative feedback from Vout to ground, Vout to negative terminal, okay? So there is a feedback from Vout to the terminal, negative terminal, which is called inverting terminal. So it is a negative feedback. So I can say that transistor is I can say virtual ground is working here. So V positive is equal to 0 volt. Same voltage will come here, 0 volt, right? Since the op-amp is in negative feedback, that's why due to virtual ground principle, V positive is equal to V negative, which is 0 volt, right? Now let the node will be X. We will apply a nodal at the point X. So nodal at point node X. So this voltage is 0 volt, right? Due to the virtual ground principle. So 0 minus V in by R plus 0 minus here minus Vref, right? Minus Vref. So minus Vref by R, okay, plus 0 minus V out by RF is equal to 0. Simplest minus V in by R plus Vref by R is equal to V out by RF. So what is it is asking? What is the condition for V out is equal to 0? So let's put let V out is equal to 0. Okay, to put this condition in equation 1. So this implies minus V in by R plus V ref by R is equal to 0. This implies V in is equal to V ref. Okay, so the option A is correct. Okay, see guys, this is the solution. You will get 1 mark. Okay, without doing all this mathematics also, you can know the answer. How guys? You see, from V in to V out, I have R and RF. Again, from V ref to V in, I have R and RF. So the circuit is symmetric with respect to two sources. One is connected positively, another is connected negatively. So since the circuit is symmetric for the two sources, okay, the two sources seeing the same circuit, right? So definitely for making my output 0, this should be equal, right? Because V in is saying the same thing, V ref also is saying the same thing. Only thing is it is connected negatively, right? That means for making V out, V in should be equal to V ref. So simple logic you can apply to solve this. You can get it in 2 seconds only. Okay. So we'll solve the next question, right? What it is asking in the circuit. So what it is asking, okay, for the transistor M1, okay, M1, mu1 COX is equal to 100 microampere per volt square, okay, mu1 COX is equal to 100 microampere per volt square, okay, double by L is equal to 10, right? Mu1 is the mobility of the electron and COX is the oxide capacitance for unit area. W is the width, L is the length. You already know this thing, right? So now the channel length modulation coefficient is ignored. That means lambda is 0. Okay. If gate to source voltage is 1 volt, so what is given? VGS is equal to 1 volt. Okay. to keep the transistor at the edge of saturation. Okay, then find the threshold voltage Vt of the transistor. Okay, see, first to understand what is edge of saturation. Okay, so if I want to plot the ID-VD characteristic of the MOSFET M1, you will see, suppose this is ID, this is VDS. Okay, you will see when I increase my drain to source voltage, the current will start increasing slowly. After a particular point, current will saturate and it will not increase at all. Okay, for VGS is equal to suppose 1 volt I apply. Okay, the point, okay, the point where the current starts saturating, it's called, this point is called edge of saturation. Okay, at this point, okay, VDS is equal to VGS minus VTH. VTH is nothing but threshold voltage. In this question, VGS is equal to already 1 volt given, 1 volt minus VTH. Okay, and at the edge of saturation, the current through the device is called saturation current. Okay, which is given by, this is ID. Okay, this ID in saturation is given by half mu n Cux double by L into VGS minus VTH whole square. Okay, into 1 plus lambda VDS. Since lambda is equal to 0, I am not putting that part. 1 plus lambda into VDS, lambda into VDS. Okay, here lambda is equal to 0. Okay, now what is the condition of saturation? The condition of saturation is VDS equal to VGS minus VTH. Okay, only at this point, this is the point where it will start saturating. Okay, the transistor will enter into saturation. The point, at this point, VDS is equal to VGS minus VTH. So this is drain, this is source. What is VDS? So the current flowing through the transistor is ID, right? ID. So the VDS is nothing but VDD, nothing but 3 volt here, minus ID into RD, right? VDD minus ID into RD is nothing but VDS equal to VGS minus VTH, right? So now let's solve it. This implies what it is showing, 3 minus ID into RD, 3 minus ID, ID nothing but, let's write the equation again, ID into RD, 3 minus ID into RD is the VDS equal to VGS minus VTH is equal to VGS minus VTH for the transistor to be at the edge of saturation. This implies 3 minus ID is nothing but half mu1 Cux double by L VGS minus VTH whole square into RD, okay, is equal to VGS minus VTH. So let's apply all the values, right? 3 minus half into mu1 Cux is 100 micro ampere per volt square. So 100 micro ampere per volt square. Double by L is 10, right? VGS is 1 volt already given. I have to find out VTH, okay, into RD is given how much? RD is 20 kilo ohm, right? RD is 20 kilo ohm into 20 into 10 power of 3 is equal to VGS is 1 volt minus VTH. Okay, so in this equation, there is only one unknown, okay, VTH. So we can easily find out. So let us do quickly. 3 minus Okay, if you see half 2 get cancelled, 10 10 to the power 3 10 to the power 4 10 to the power 4 800 10 to the power 6 10 to the power 6 minus 6 get cancelled, so I will get 10 into 1 minus VTH rho whole square, right? 10 into 1 minus VTH rho whole square, okay, is equal to 1 minus VTH. So let's solve now. It is 3 minus 100 into 1 plus VTH square minus 2 VTH equal to 1 minus VTH. This implies 3 minus 10 minus 10 VTH square minus 20 VTH is equal to 1 minus VTH. Okay, take everything to the right. That means 10 VTH square minus 21 VTH, right? So minus 10, here it is plus, right? Minus minus plus, okay, minus 21 VTH, okay, plus 3 minus 10 minus 7 a plus 1, so is equal to 8 is equal to 0. This implies VTH square minus 2.1 VTH minus 0.8 is equal to 0. This implies VTH minus 0.5 into VTH, let us do the partial fraction, okay, minus 1.6 VTH minus 0.8 equal to 0. Okay, this implies VTH minus 0.5 this implies what you have to do, okay, if I take VTH common, okay, I'll get VTH minus 0.5. Here I will take let's take 1.6 common, I will get VTH minus 0.5 is equal to 0. This implies VTH minus 0.5 into VTH minus 1.6 is equal to 0. This implies VTH is equal to 0.5 volt or 1.6 volt. Okay, so you see VGS is equal to 1 volt. Okay, already 1 volt it is given. Okay, so for my transistor to be on, we know VGS should be greater than or equal to VTH, right? So when if I take 1.6 volt, this equation will not hold. Okay, so since my if I take 1.6 volt, this equation will not hold and the transistor will not turn on. Okay, so 0.5 volt is the answer, because if I take 0.5 volt, in that case VGS, which is nothing but 1 volt, is greater than 0.5 volt. So the answer is 0.5 volt. Okay. So we will solve another question. Okay, you see an asymmetrical periodic pulse of Vin of 10 volt amplitude with an on time of 1 millisecond, okay, and uptime of 1 microsecond, okay, is applied to the circuit shown in the figure. Diode D1 is ideal. Okay, so what you have to find out? Find out the difference between maximum voltage and minimum voltage in the output waveform V0. Okay, so first you understand there is an input pulse. Okay, so let me draw the input pulse. Okay, what is my input pulse? It is on for 1 millisecond. Okay, off for only 1 microsecond, very, very short time, right? So it is on for a longer time, okay, off for very small time, okay. So I'm just exaggerating to show you, but it is very, very small. Okay? I'm just exaggerating to you. I'm just exaggerating, okay. So this is 1 millisecond, right? And this is 1 microsecond. So very, very small. But for showing to you, I'm just exaggerating. Okay. This is my V in. Then it is again on. Right. So it will continue like this. Okay. First you understand how the circuit is operating. Okay. When V in is 5 volt. Okay. It is how much? 10 volt. Suppose it is 10 volt. 10 volt. When it is 10 volt. Okay. The diode will be on. Right. The diode will be on. And the capacitor will charge. Okay. So then V in is equal to 10 volt. What is the circuit? Circuit is the diode will be forward biased, right? And the capacitor will charge. We know for a ideal diode, when it is forward biased, the it will behave like a short circuit. Okay, so the equivalent circuit will be capacitor is there. Okay, there is a resistance. Okay, and the diode will behave like a short circuit in forward bias. Okay, then I apply V in 5 volt. 5 volt, 0 to 5 volt in this point. Okay, it will behave like a short circuit. Okay, so the capacitor will charge through this path. Okay, but the time constant this is 20 nf. Okay, so the time constant tau is equal to r into c is equal to 0 into c, because it is short circuit. Okay, my output is, my time constant is 0. Okay, so the capacitor will not take any time to charge, so it will charge instantaneously because it is charging through a short circuit. Okay, the time constant is r into c is 0, so it will charge instantaneously to 10 volt. Suppose, so sorry, it is 5 volt, right? It is 10 volt, it is 10 volt, 10 volt. Okay, so if I draw the waveform at the capacitor, how it will be? See, when V in 10 volt, it is charged through this diode, which is ideally short circuit. Since the time constant is 0, it will charge instantaneously. Okay, and V in will be, if I draw the VC, nothing but voltage across this capacitor. Okay, it will charge instantaneously to the 10 volt. 10 volt, right? It will charge 10 volt and it will stay at the 10 volt. Okay, and the time to go 10 volt is 0 because time constant is 0. Okay, now when I apply input 0, right, the diode will be reverse biased, and in reverse bias diode behave like a open circuit. So when V in is equal to 0, okay, for 10 microsecond, sorry, 1 microsecond, right? 1 microsecond. Okay, second. What is the circuit will be? You see, plus or minus V in. The capacitor is already charged to 10 volt. 10 volt. Diode will be open circuit. Okay, this is V out. Okay, so you see, now V in is 0 means it is 0. 0. So the capacitor will discharge through this resistor of, what is the resistance value? Is 500 kilo ohm. Kilo. Okay, so it will discharge through this resistance 500 kilo ohm for 1 microsecond. Okay, what is the time constant of discharge? R into C is 500 kilo, okay, into 20 nano into 10 power of 9. Okay, if you do it, it will come, okay, 5 into 2, 10, it will come 10 millisecond. Okay, so the capacitor needs 10 millisecond to discharge completely, approximately completely. Okay, so since my discharging time constant, it is discharging through this resistor. Okay, RC is 10 millisecond. It will take approximately 10 millisecond to discharge, but it is V in is 0 only for 1 microsecond. Okay, 1 microsecond. So it will not discharge at all because I need 10 millisecond for discharging, but I am applying 0 volt in the V only for 1 microsecond. Okay, so my time constant tau is far greater than my time of discharge. Okay, discharging time, discharge time. Okay, so it will not discharge at all because it need 10 millisecond. I am applying V in 0 only for 1 microsecond. So the discharge will be approximately 0. So the capacitor voltage will stay at the same value. Right? Now, what is V out? V out is nothing but V in minus Vc. This is V in. Okay, V in minus Vc is equal to V in minus Vc is equal to V out. Okay, so let's plot it. Suppose plot V out. V in is this one, V out is Vc is this one. Okay, so 10 minus 10, so up to 1 millisecond, V out will be 0, right? At this point, V in is 0, Vc is 10, so I will get minus 10 for 1 microsecond. This will be minus 10. The duration will be 1 microsecond. Again, it will go to the 0 volt, right? What it is asking? The difference between maximum voltage and minimum voltage of the output waveform. So what is the maximum voltage? Is 0 minus minimum voltage is minus 10. So I will get 10 volt is the difference between maximum to minimum voltage in the output. Again, I am just summarizing. Then V in is equal to 10 volt. It will charge quickly through a time constant 0. So I get 10 volt. Okay. Then V in is equal to 0 volt for only 1 microsecond. It will not discharge at all because it need 10 millisecond to discharge to the resistor of 500 kilo ohm. So the time constant for discharge is far more than discharge time. So the capacitor voltage stay at 10 volt. Okay. Now we have to plot V in minus Vc is output. So we have seen we'll get a 10 microsecond pulse for only 1 microsecond. Okay. We got a pulse of negative 10 volt of only 1 microsecond. Okay. So the answer is 10 volt. So another question. The circuit with an ideal op amp, okay, shown in the figure. The pulse V in is of 20 millisecond. This is 20 millisecond applied to the input. Okay. The capacitors are initially uncharged. Okay. Find out the voltage V out at T is equal to 0 plus. Okay, guys. Since the capacitors are uncharged, I am applying a transient voltage from 0 to 5 volt. Okay. So for any transient, the capacitor will be like a short circuit when it is initially uncharged. Okay. So you see, this is the equivalent circuit at T is equal to 0 plus. Since capacitor will be like a short circuit. Okay. So I will get the circuit like this. Okay. For the tangent duration at 0 plus, the capacitor will be like a short circuit. So this is the equivalent circuit. So it is asking to find out the V out at this particular instant. Okay. You see, first thing is, guys, can you tell me it is positive feedback or negative feedback? Okay. You see, output, there is a connection from V out to negative. Okay. But be cautious, it is not negative feedback. How? I will tell you. Okay. Suppose you take a non-inverting amplifier. Okay. Okay. Let it be RF. Let it be RI. I'm applying a VIN. VIN. Okay. Guys, this is my V output. If I want to calculate what is the feedback from V output to negative terminal, what I have to do? I have to sort my VIN. Okay. For calculating beta feedback factor, I have to sort my VIN minus plus I have to sort the another input. This is my RI. Then there is RF. This is my V out. Okay. What is the feedback factor beta? Beta is equal to RI, right? RI, sorry, RI by RI plus RF. That means V means some part of the output. How much it is? V out into RI by RI plus RF. So this is my feedback factor beta. Okay. So now if Ri is equal to 0, what is the beta feedback factor? 0 by 0 plus Rf is equal to 0. That means there is no feedback, right? When I make it 0, there is no feedback. So you see in the circuit, if I want to calculate the feedback, what it will be? I have to replace V into 0, V into 0. There is a ground and there is a 110 kilo ohm. Okay, V out 10k. You compare this circuit and this circuit when Ri is equal to 0. That means beta is equal to 0 by 0 plus 10k is equal to 0. That means there is zero feedback. There is no feedback. Okay. So you can say this circuit is with zero feedback, not negative feedback. Okay. That means so feedback equal to 0. Okay. So if you see how to calculate the V out, okay, you see here feedback is 0. Okay, that means it is not negative feedback. Okay, and in this circuit, okay, in this circuit V in is equal to V in is equal to 5 volt. Okay, V in negative is equal to 5 volt. Okay, V in negative is equal to 5 volt. V in positive is equal to 0 volt. Okay, since there is no feedback, it will behave like a comparator. Okay, so V out is equal to gain into V plus minus V minus. Gain here is how much? It's ideal op amp, so infinite gain 0 minus 5. Okay, so I'll get minus infinity. Okay, so V out is equal to ideally minus infinity, but it cannot go to minus infinity. It will saturate at minus 12 volt, which is the highest negative supply. So it will saturate to minus 12 volt. Okay, it cannot go negative more than minus 12 volt. Okay, so it will saturate to minus 12 volt because my negative supply is minus 12 volt. So the answer is minus 12 volt, and the summary is here the feedback is 0. Because the feedback is 0, it behaves like a comparator. For a comparator, the output is gain into V positive minus V negative. So infinity gain into 0 minus 5 nothing but minus infinity. Since circuit will cannot go to minus infinity, the output is saturating to minus 12 volt. Okay, so that's all for this 2021 examination. Okay, thank you guys. See you.